In this video, we would be talking about the way the world works, focusing on the scientific knowledge. Let's talk about some of the observations we have of this world. Many things occur in the same way over and over. These are called regularities. One example is that the sun rises in the east, not in the west. Another is that iron rusts or nangangalawang but gold does not. Lastly, chicken lay eggs, while dogs don't, since they, as we know, give birth. On the other hand, we have irregularities. So these are the very opposite of regularities. One example is that some trees bear fruits like mango trees and avocado trees, while some trees do not, like Nara. So if all experiences are as irregular, we would not know what to expect next. Past experience would provide no guide to the future. Next, we have invariable. So these are the conditions under which a certain type of event occurs without exception. We often search for genuine invariance in nature. One example is that when we always think that the boiling point of water is at 100 degrees Celsius. Pero kung pupunta tayo sa mountaintop, we would find out that it's less than 100 degrees Celsius. Upon repeated observations, we can find out that the boiling point of water is not based on the temperature or sa panahon, init ng panahon. It's not also based on the moisture of the air, but it's actually based on the pressure of the surrounding air. So that's one example of when we search for genuine variance in nature. Next, we have the question, why are we interested in discovering these irregularities? The answer is that because we are interested in predicting future events. Regularities and irregularities help us predict the future. And if we can predict them, then we can act in accordance with the prediction. So one example is that by experience, we know that some snakes are poisonous, like vipers. So when we go in a, or when we're in a situation where we see a viper, then we know what to do, which is to run away or to get away as far as we can, since they are poisonous. So that's one of the reasons, or mainly the reason, on why we are interested in discovering these. All in all, science is the systematic search for uniformities in the way things behave. And these uniformities in the way things behave is what we call the laws of nature. Moving on to the laws of nature. Usually, when people talk about law, they mean an edict that has been issued by a head of state or enacted by a legislative body. But actually, laws in this sense are prescriptive laws. Prescriptive laws prescribe how the people within its jurisdiction are supposed to behave or not behave. In other words, these are the do's and don'ts. One example is the Child Protection Act or the Republic Act number 7610. On the other hand, we have descriptive laws. These laws provide descriptions of how. So since laws of nature is a descriptive law, it means that this law simply provides descriptions of how nature works. One main observation of these two laws is that only conscious beings can prescribe, since only they are capable of giving orders. So prescriptive laws will not exist unless there is someone capable of giving orders. However, the uniformities of nature would still occur even if there were no human beings to describe them. With that, we can now avoid several confusions regarding the laws of nature. First, laws should be obeyed. Whether or not you should obey all the laws of the land is a problem in ethics. But a law of nature is not the sort of thing you can obey or disobey, since it is not an order or command anyone has given. Your emotions or our emotions, along with those of stones and rocks and every particle of matter in this universe, or in the universe, are instances of this law. But since the law only tells us how matter does behave, and doesn't prescribe how things should behave, you cannot be said to either obey or disobey it. Second, when there's a law, there's a lawmaker. Again, this applies to prescriptive laws. If a course of action is prescribed, someone must have prescribed it. But laws of nature are not prescriptions. They only describe how nature works. Third and last, laws are discovered, not made. This applies only to descriptive laws. We discover how nature works, we do not make it work that way. However, the formulation of these uniformities is the work of human beings. When can a statement be considered a law of nature? First, a law of nature is a universal statement. It is in the form of all A's are B's, or if something is an A, then it is or has B. A simple example is all iron rusts when exposed to oxygen. Another example is that all copper conducts electricity. However, if not all A is B, but only a percentage of A's are B's, we have what is called a statistical law. Second, a law of nature must be open-ended. It must have an unlimited range in time and space. Whenever and wherever there is an A, it will be or have B. For example, wherever there is iron, it is magnetic. Thirdly, natural laws must be expressible as hypothetical statements. Conditional or hypothetical statements are in the form of if-then statements. These statements describe how the world works under certain conditions or circumstances. If this were a stone, it would fall if we let it go. We would have to put in a few qualifiers, such as that the stone must be within the gravitational field of some star or planet, and not out in the midst of space somewhere. Because in that case, hindi siya mahuhulog. And that the atmosphere must not be of greater specific gravity than the stone. We are confident not only that stones do fall, but that if we were to release a stone, specifying the conditions first, then it would fall. Fourth and last, the greater the generality of a statement, the more likely it is to be accorded the status of a law of nature. Laws about the melting point of various metals are sometimes called merely low-level generalizations. If the melting point of lead were different from what it is, this would not affect much else in the universe. If some birds had 3 legs, this would also not affect such much besides birds. However, if there is friction, then there will always be heat. Seems to be more fundamental, since friction generates molecular motion, and heat, in the physical sense of the term, is molecular motion. Next, we have the explanation. Scientific knowledge enables us to explain why many things occur as they do. However, explanations are not always answers to the question why. Sometimes they are a request for clarification. So, for example, a teacher asks you to explain a passage in a poem, or when someone asks you, "What are you doing?" Those are examples of asking for clarifications, and in return, we give explanations. Sometimes, when we give an explanation, we just tell the inquirer how we do something or how a device works. Moreover, the sciences are most concerned with explaining the why of events, so we may ask why a particular event occurred. Finally, we have theories. Theories are never proved. They are not absolute truths or facts. While yes, they are supported by a substantial amount of empirical data and experimentation, they can never be proven with absolute certainty. Also, they are always subject to revision in light of further investigation. Science, as we say, is an ongoing process, and as new data and research emerge, our understanding of natural phenomena can evolve. Scientific theories are dynamic and subject to change or refinement in the light of new information or improved methodologies. Lastly, theories can provide an explanation of the observed facts. Scientific theories can bring together various pieces of evidence and observations into a one unified and logically consistent explanation. A theory in astronomy. When we look up at the sky at night, we see the moon, the planets, and stars moving steadily across the sky from east to west, setting and then rising again some hours later. They all go around the Earth. This has seemed such an obvious fact to most people throughout human history that anyone who thought differently was considered mad or crazy. The Earth, or the place we are standing on, is, or what seems to be, the center of the universe, and the celestial bodies revolve around it. The ancient Greeks and Arabs noted that the sun, moon, and planets move about among the stars, whereas the stars, although they move across the sky, never showed any apparent change of position in relation to one another. The pattern of the constellations remained the same. The sun and moon and each of the five visible planets were each infixed on the interior surface of a hollow crystalline sphere, and each planet had a sphere of its own, since each of their relative motions was different. The stars were all fixed on the interior of the outermost sphere, and this theory of the crystalline spheres seemed only a slight remove from obvious observed fact. On the other hand, the Egyptian astronomer Ptolemy noticed some peculiarities in the motion of the planets. Ptolemy believed that the circle was the only perfect curve and that all the celestial bodies moved in circles. But, but if we are going to imagine them traveling in little circles around the big circles, which we call then the epicycles, then we could account for the apparently erratic retrograde motions of the planets. Every time more careful observation showed another slight variation in a planetary motion, the new motion could be explained by introducing another epicycle, or another small circular orbit around a larger one, which in turn circled around another larger planet, or another larger epicenter or epicycle. There was no general theory that could predict that the planets would move in epicycles. But once the theory was accepted, it was possible to use it to track the path of the planets through the years and even predict their future location. Even eclipses were predicted by this theory. However, even today, no one believes this theory. We also have Copernicus, who held that the Earth, along with the other planets, goes around the sun. If we assume this, you could account for the small motions, including the retrograde motions and even the larger motions. The Earth, being closer to the Sun than the Jupiter, moves more rapidly in its orbit. When it is rounding a bend in its orbit, the more distant planet will appear for a time to be going in the opposite direction. Just as to the driver of the fast car on the racetrack, the slower driver on the outer track appears for a time to be going in the opposite direction. Here then was a simple and plausible explanation for the observed motions of the stars and planets through the sky. As we also can observe, however, there was no difference between them. Both theories, Ptolemy's and Copernicus, explained the same observed data. The only difference maybe was that the Ptolemaic theory was more cumbersome or more complicated. However, for the Copernican theory, there is something that was somehow tried to falsify the theory. If the Earth were going around the Sun in an orbit, this concludes that there should be a slight difference in the apparent position of the nearer stars in relation to more distant ones. This is called the parallax. But in spite of careful telescopic observations, no such parallax was observed. Copernicus standed by his view and did not abandon the theory. He stated that the stars must be so distant that no parallax could be detected. Now, if the two theories both explain the same set of observed facts, then the theory that is simpler, in the sense of requiring fewer principles, is the one likely to be accepted. This leads us to simple theory. If it turns out that the simple theory is inadequate or that it cannot explain the facts discovered later, then the simple theory must be scrapped. However, if it explains all that is required, then it is accepted. This is actually what Occam's razor states. Accept the simplest theory that explains all the known facts. Simple theory is neat, tidy, elegant, and aesthetically pleasing, which is actually the long goal of science, to explain as much as possible by means of as little as possible. In theories, we only infer from the observed motions. The revolution of planets around the sun is not observed fact, but actually a theory. However, it is a highly confirmed theory due to the heliocentric theory, the theory that the sun is the center of the solar system and that the planets revolve around it.
Next theory is a theory in geology. This involves aspects of scientific inquiry and the interconnected nature of scientific knowledge. According to fossils, the dinosaurs suddenly disappeared way back 65 million years ago. This piqued the interest of geologists, biologists, astronomers, and paleontologists to find an explanation of the event. Geologists have found two clues. First clue is a thin layer of clay that was discovered in Italy at the boundary between the Cretaceous and Tertiary periods, corresponding to the time of the dinosaurs' extinction. Unusually high levels of iridium, a rare metal on Earth's surface, were found in this layer. Two theories were proposed to explain the presence of iridium. First is the volcanic activity, and second is the collision with an asteroid or comet. And the second clue, geologists found grains of quartz in clay layer with cracked and strained features. These are similar to those found near meteorite craters, nuclear bomb test sites, and the moon. These features could only be formed by extreme heat and pressure from a powerful explosion. Also, for biologists, they have identified a recurring pattern in the extinction of various animal species over the past half-billion years. These extinctions occurred in cycles with a periodicity of about 26 million years ago. It is followed by the astronomers that attempted to explain the 26 million year extinction cycle by considering extraterrestrial factors such as solar flares, supernovae, and the sun's invisible companion star. To relate this to dinosaurs' extinction, the extraterrestrial factor called the Oort cloud comes to the picture. It is a region beyond Pluto that contains many comets. Astronomers hypothesize that the Sun's invisible companion star, with a highly elliptical orbit, intersects the Oort cloud approximately every 26 million years. This interaction causes comets to be drawn into Earth's orbit, leading to a dust cloud that blocks sunlight and results to mass extinctions. The 26 million year cycle has been confirmed multiple times, but the Sun's dark companion star remained a missing link. It remained unconfirmed. Astronomers estimate a 1 in 3 chance of finding it. If it were achieved, the cometary theory would be much more highly confirmed. This states three things. First is the accounts emphasizes the interconnected and coherent nature of empirical science, where facts, laws, and theories are interdependent. Meaning to say, if any inconsistency within the scientific system must be resolved, it may involve revising theories or reinterpreting facts, and so forth. Second, the testing procedures are interdependent. Correlations between testing procedures has been long confirmed. In determining the temperature, for example, we assume that there is a correlation between a rise in temperature and in mercury of the tube. Third, scientific theories often rely on assumptions that are consistent with already confirmed theories. Assumptions are made when evidence points to the coherence of a theory even when certain aspects are unobservable. The extinction involves multiple hypotheses. Iridium rocks, Earth craters, and meteorite impacts are all observable phenomena. We rely on our current observations to make inferences about past events. Since we cannot directly witness these ancient occurrences, we can consider them as theory. Therefore, statements about dinosaurs are considered theoretical because they pertain to events too remote in time to be observed through our senses. A theory in physics: when scientists cannot explain the things they observe by means of other things they observe, they attempt to explain the observed by means of the unobserved, and sometimes the unobservable. This is what happens in dealing with the ultimate constituents of matter. Ultimate constituents of matter are not observable by our senses or instruments. It could be considered non-existent. However, most physicists are deeply concerned with understanding the composition of material things down to these ultimate constituents. Electrons, for example, are inferred entities, yet they are believed to exist based on their role in explaining various phenomena. The ancient Greek philosopher Democritus and his follower Lucretius proposed an early atomic theory to explain the behavior of matter. Lucretius proposed an atomic theory to explain the behavior of matter in his poem on the nature of things. His theory suggested that matter is composed of tiny indivisible particles, that is called atoms. Lucretius used examples like how stone steps wearing away, berry juice diffusing, and sugar dissolving to support the idea of matter consisting of tiny particles. These examples illustrated that matter must be made up of tiny particles that cannot split any further. After the ancient atomic theory, more refined atomic theories involving protons and electrons have been devised to explain these countless facts. This inferred the limits of explanation in science. The limitations of scientific explanation become apparent when we realize that the chain of explanation never reaches a final ultimate answer. Second, this culminates in the concept of a brute fact, a fundamental aspect of reality that lacks a comprehensive explanation. Third, despite having explained numerous phenomena using scientific laws and theories, the ultimate constituents of matter and the fundamental laws of the universe remain unexplained. Fourth, Einstein's pursuit of a unified field theory aimed to encompass multiple physical forces in a single framework, but this would still rely on unexplained principles unless further clarification is done. And lastly, this emphasizes the mystery that science confronts as it strives to fathom the deepest aspects of the universe. Emergence and reducibility. First, let us define what is emergence. It refers to the idea that certain properties in complex systems cannot be predicted to the properties of their simpler components. These emergent properties emerge at higher levels of organization and are not evident from the knowledge of the lower level components alone. Example, we have this meme of SpongeBob in chemistry. We have sodium as an explosive metal and chlorine alone as a deadly gas, but combined together, it is just the edible salt. The properties of salt cannot be entirely deduced from the properties of its chemical components, sodium and chlorine. Reducibility, on the other hand, refers to the extent to which a higher level system can be logically deduced from or explained by a lower level one. It is the idea that complex systems or phenomena can be broken down into simpler, more fundamental components or principles. Example, physics being reducible to mechanics, or inorganic chemistry being reducible to physics. However, the point is made that this reducibility does not seem to apply to biology, particularly in terms of explaining the transition from inorganic matter to living organisms. When reductionism is successful, it means that complex systems can be broken down into simpler components and their properties be deduced from the lower level principles. Emergence is when the properties of a higher level system cannot be fully explained by reducing it. That is why emergence only occurs when reductionism is not successful. This leads us to the emergence of teleological explanations. It centers on the idea that living organisms, particularly their behaviors and consciousness, are at higher level of reality and are not reducible to the properties of inorganic matter. This claims that no amount of knowledge about inorganic chemistry and physics can logically deduce propositions about living things. Explanation in biology. We constantly employ the concept of purpose when discussing living organisms. Living things are often described as if they have purposes and intentions, which is a common way to explain their actions. Purpose can be understood in different ways. First is why people do what they do to carry a purpose in mind. For an instance, someone will ask, "Why did you leave early?" And their answer happened to be, "To study in the library." Second, the intended function of a non-living object reflects from their human makers. Example, a hammer's purpose is to pound nails. But hammer itself does not hold a purpose. It is the human beings who have the purpose of making the hammers. Third is the function or role of biological organs or structures in the body where it is not made by humans. Example, the heart's purpose is to pump blood. Um, Biologists and physicians focus on the functional aspects of organs and organisms, not conscious motivations or divine purposes. Which leads us to the debate with the creationism or the religious explanation of the existence of living things. Creation versus evolution. For creation, creationists believe that the probability of life arising from inorganic matter is zero. The intricacy of a living organism's ability to sustain life is of such immense magnitude that it seems implausible for it to have arisen from any conceivable combination of inorganic molecules. Second point is that God is credited with having brought all living entities into existence, as well as being the creator of the universe and everything it encompasses. For evolution, evolutionists acknowledge that the conditions necessary for the evolution of living things may be rare. However, over the last 50 years, there has been significant progress in understanding biochemistry and environmental conditions of when life began. Evolution provides a coherent explanation of how living things evolve over time. This progression is based on the fossil record and scientific evidence that served as a crucial piece of evidence in support of the theory of evolution. Evolution is a concept discussed by scientists because it is subject to scientific testing and verification. In contrast, creationism is not discussed within the scientific community because it falls outside the realm of science. Theological beliefs are considered separate from the empirical and testable aspects of scientific inquiry. With what we have discussed, we conclude this revealed how laws of nature, explanations, and theories have impacted the scientific knowledge in existence. That's all about the way world works. Thank you for listening.